Today we're going to do some ROM hacking to modify this into this. So today we're going to do some C64 ROM hacking modification kind of thing, and I am going to use my emulator that I've written in C#. This is by no means a full-featured emulator, but it's more than enough for this case, and it has some... Having access to the source code makes it easier to do some of the stuff we're going to do today. So the first thing we'll do is to, just for fun, try and change this string at the top here, which says Commodore 64 Basic V2. And that should be pretty easy. I usually use this online hex editor to do, to modify binary stuff, because it's actually pretty good, at least for a web-based hex editor. So this is hexedit or hexed.it. As you can see here in the editor, I have kernal.rom open, which is the kernel ROM in a C64, and this is the kernel ROM that I'm using for my emulator. So whatever changes we do in here is going to be reflected when we start the emulator. So we're looking at the contents of the ROM here, and it's going to be a mixture of assembly, machine code, and different kinds of data, strings and stuff like that. Let's just start by seeing if there's any... there we go. So just by browsing we can actually see some text there. So I could also do Commodore, and we'll find that string that I was talking about, Commodore 64 Basic V2. So let's just start by modifying this to HAG'S LAB. And that even fits in there perfectly. So let's just do a save. I'll save that on top of the kernel ROM that my emulator is using. I'll switch over to the emulator. And there we go. HAG'S LAB 64 Basic V2. So that's pretty easy to do. It's Christmas, so I thought we would do some kernel decorations and make the C64 a little bit more Christmassy. I thought we could change the border color, the frame color, the background color, and font color, just to get a Christmas theme going. As you can see, I have some more tabs open and ready here. I have a color in the C64 wiki, which shows us all the colors of the C64 and which value that corresponds to each color. So we're gonna need that. So if you're gonna use white, which is 1, and red, which is 2, and maybe green, which is 5. And the original colors are 6 blue and 14 light blue. So that's going to be 6 hex and E hex. I also have the Commodore 64 memory map. And as we can see here, we have these two addresses, which I'm sure a lot of you know. These are addresses that you can easily poke in BASIC to change the colors. And I also have the 6502.org site, which is a pretty good index over all the opcodes of the 6502. So what we're gonna have to do is figure out what we need to change in the kernel to change the default colors. So there are different ways to do that, but I thought we could start by looking at some source code for the kernel. This is Mist64 on GitHub, which has the C64 ROMs available. So here we can actually have a look at the source code for the kernel. What we can do is do a quick search inside here. So let's just do color, and we can see that we actually find some stuff here. So this right here is going to be an interesting comment. It says init color to light blue. So in editor 1, just find it, there we go. So in this editor1.s file, we can see that we have a load A, which says init color to light blue. And then it just stores that into a color variable, which is defined somewhere. And this makes it pretty easy for us to try and find this in the binary image. Because we know we're looking for a load A instruction with the value E, which we remember is light blue. So that makes sense. And then we're looking for a store A afterwards. If we then have a look at the 6502 opcode index, we can do load A, and we can see that we have different kinds of opcodes, and that's because they have different kinds of addressing modes. But we know which mode this is because we have this way of typing an address means it's an immediate value. So this means that we're using this version of load A, which is the immediate load A instruction. And as you can see here, the value actually shows in the same way as it does in the listing. So that means we're looking for instruction A9, and it should be immediately followed by E hex. So we can just do that to start with. Just look for those 2 bytes in the image and see if we get a hit. So that's going to mean we need to search for A9 and E. So let's go back into the hex editor and we'll do a search for A9 0E. Okay, so we find two locations. One of them are in the opposite direction, so that's not going to be what we want because we know the opcode is going to be before the operand, which is the value. So it's actually going to have to be this first one. If we take a look at the byte following these 2 bytes, we have an 8D, which is probably going to be the store A. Yeah. So there we have it. So 8D is the store A, which comes next. And that's an absolute addressing mode instruction. So it looks like we're in the correct place. So if we change this value to some other value in this table, we're going to hopefully change the default color of the text. Let's say we want to make that white because that makes it easy to read, and it's one of the colors we want to use, the white, red, and green. So let's go with white. So let's change that to a 1. Which is easy, we just type 01. And then we do another save. Jump into the emulator again. And there we go. we have white text. The default light blue on blue is kind of, I don't even know why they did that. They should have used white as the default color because it's so much more readable on a screen. So this is a nice hack to actually do on your C64 and not just a fun trick like we're doing today. This is actually useful. So next we're gonna have a look at these other colors, the frame color and the back color. And I'm sure we could use this source code to find those values as well, but let's just, for fun, let's do it in some other way this time. So if you have a look at the Commodore 64 memory map, it's D020, which is the border color, and it's D021, which is the background color. So if we do some pokes here, we can do poke. Let's do the border color, which is 53 to 80, and we can do, was it 2? That was red. So let's just try that. There we go. So that gives us a red frame, and we can do the same to get green. We can do 5. There we go. Or we could do a poke. Let's do the background color next, 53281. Let's do red on that one. There we go. So that looks kind of Christmassy, I think. So that's gonna be our Christmas theme for the kernel. So we're gonna try and make the kernel look like this on startup. Even though these addresses control the looks on the screen, they are not part of the kernel. So these addresses get initialized by the kernel using some value inside the kernel ROM. So we have to find out what is writing to these values when the kernel starts. So it's pretty easy to do when we have an emulator. We're just going to use Visual Studio and have a look at the code and use some debugging features inside Visual Studio to do this. We'll go back into Visual Studio. The parts we need to look at today is the CPU implementation, which is this code right here, and the C64 bus implementation, which is the code that controls the bus mastering basically, and the all the addressing on the bus. So it makes sure the C64 sees the different hardware and RAM and stuff like that, RAM and ROM, at the correct places. So inside this bus, we have a, let's see if we can find it. There we go. We have a write method. And whenever there's a write to memory, to RAM, well, actually any kind of memory, but it's a RAM in this case, this method is going to be called. And I put some code here already that we can just uncomment. And it says that if something is writing to address 0xD020, which is the border color, then we will write a debug message that says there was a write to that address and which value it was. So this is just going to give us a couple of debug messages. Let's see what happens. So there we go. So it's already started up and we should be able to see these messages. So if I just change to this window right here, we can actually see write to address D021 value 6. So that's going to be blue. So D21 is going to be the background color, which is blue. The other one is going to be D020, which is E. And that is going to be the frame color. So we can see that the kernel is actually writing these two values into these memory locations on startup. Now, what we need to do is find out what actually does this write and where that write takes this value from. So to do that, we can just make a breakpoint in here. When the kernel actually does the write, this is going to pause the whole application, and we can have a look at what's happening at that point. There we go. So we can now inspect some values. So the address is currently D020, which it has to be because we're inside this block. And the value that's being written is 0E. So if we have a look at the call stack of the application, we can go one method back and we'll see that we're in the CPU now. And this is where the CPU does the write to memory. But we need to go one more method back in the call stack, which takes us to a store A instruction. And what's currently in A, the A register in the CPU, is the value 0E. So to figure out where this is happening now, we have to take a look at some other registers of the CPU. And what we're interested in is the program counter. And the program counter is currently at E5B0. So that's going to give us a hint as to where in ROM the code that is executing now is located. And this first E we can actually just discard, because we have to do minus E1000 hex on this value to find the correct offset in the kernel ROM, because the kernel ROM is mapped into E1000 in the C64. So if we then go to 5B0 in our hex editor, let's just go to, what was it, 5B0. So that's right here. But what's actually happened now is that the program counter has been incremented to the next opcode already, because our CPU has already done the retrieval of the operands and stuff like that, and that makes it increment the program counter. So we're gonna have to go back a little bit, and we know that we're looking for a store A, and if we then have a look at the different store A opcodes, so we have 85, 95, 80, 90, 99, 81, and 91. So we're gonna have to see if we can find any of these opcodes in the ROM. We can also see these opcodes in my CPU implementation. So let's go to the hex editor again, and we'll go back. So CF, not one of the opcodes we're looking for, neither is FF, but then we have 9D, and 9D is the opcode for a store A with absolute X addressing. So that makes sense. And I just realized that we can actually already see that if we have a look at the CPU implementation again. We can see that the current opcode is a store A, and the opcode address is E5AD. We do minus E1000 and then we have 5AD. And this is the current address, 5AD. So this is the store A we're looking for. But the store A is not going to give us much, because that just means that the CPU is going to store whatever is in A to the following memory address. So we need to have a look at what happens before that. We need to have a look at what loads a value into the A register, because that's the value we're interested in. And that means we're going to have a look at load A. Just as store A, there are different kinds of addressing modes. Usually when we have a store A with absolute addressing, absolute X index addressing, it makes sense if the load A is going to use the same addressing mode, because we're probably inside a loop which reads data from one address and writes it to another address. So it's initializing many values in a memory region. That's what I'm imagining here. So let's assume that the load A is going to be using the same addressing mode. So let's do load A and absolute X indexing. That's going to give us the opcode BD. We can also see that this opcode is also length of 3 bytes, including itself. So it's going to be BD and then 2 more bytes, which is the operands. So if this is the current instruction we're at, we know that the previous one is probably going to be a load A, and it is 3 in size. And I guess a lot of you already can see that we have BD right there. So this is probably going to be the load instruction we're looking for. The next 2 bytes is going to be the operands for BD. And the operands for BD is the address that the value is loaded from. So it's going to take the value at this address plus the X register and load that value into the accumulator. So to figure out which address it's taking this value from, we have to look at the operands and we have to look at the current value in the X register. So first we can have a look at the address. And what we have here is B8EC. So the address we're looking for here is actually not B8EC, but it's ECB8. And that's just how the 6502 works. So it reads the address in this order, basically. So we're looking for ECB8. And that sounds correct, right? Because we know the kernel is mapped into E1000. So it's definitely within that range. But we still need to remove that E. So we do minus E1000 again, which gives us the address CB8. That's going to be this first part. But then we have to take the X register into account. We're going to have CB8, and if we take a look at the X register, that's currently 0x21. So let's bring up a calculator, make sure it's in programming mode, and we'll do hex. So CB8, and we're going to add the value in the X register, which is 21. That gives us CD9. So if we go into the X editor again and we go to CD9, we can actually see the value of E, which is the value we're looking for. So this should be the initialization value for the border color. So let's change that to, what was it, green? So let's change that to green then, which is 5. Just do a 0, 5. I'll do a save again. Jump into the emulator. And now we have to stop the whole thing and restart, which is actually gonna hit the breakpoint again. But that's fine. We can actually inspect if we get the correct value now. So the address is still D020 and the value is 5 this time, which is what we just entered. It's changed from 0E to 05. So let's just skip past this breakpoint. And there we go. There's our green frame color. So right next to the value we just changed from E to 5, we have the value of 6, which we know is blue. So we could just make an educated guess that that is the back color. But let's just quickly go through the same process again and see if we end up at the same, well, at this value. So this time we put a breakpoint on D021, which is the background color. We wait for the break and we can see that it's writing to D021 with the value of 6. And we'll go to the call stack again. And we'll go back as we did last time. We find the store A and the accumulator is 6 this time. We'll go up and we'll find the address. So the address of the opcode is 5AD. That's the same as last time, so that basically means that this is in a loop. So it's just incrementing the X register and it's doing using the same code over and over. So let's go back to 5AD. That takes us to the same place as last time. And we have the CB8 again. So let's just do CB8. But then let's have a look at the X register. And there we go. So the X register is now 22. So that's been changed. So let's do plus 22, which gives us CDA. CDA takes us straight to that 6 value. So that is going to be the background color. So we'll have to change that, and we want the red color, which is 2. So we'll do 02, save as kernel, restart the emulator. We can verify the value in the breakpoint, which is 2. We continue, and there we go. That's our final Christmas theme. Now I think we should change this this text to something a little bit more Christmassy. So we can basically just search for HAG this time. There we go. And we'll do XMAS. Let's do Merry Christmas. Okay, so we're gonna need some more. So let's do space Merry Christmas. We can't change the size of the ROM. We have to make the text we put in there the same length as the previous text. So let's do it like this. So Merry Christmas 64, basic v2. I think we can just add a star there. Okay, let's see how that looks. Merry Christmas 64. Should probably shift the whole thing to the right. Yeah, that worked out nicely. And that looks a little bit more centered. So Merry Christmas 64, basically to 64K RAM system, 38911 basic bytes free. Nice. There we go. So the next step is to actually use this theme on my real C64. And to be able to do that, we have to take this kernel image that we made and burn it into an EEPROM. And we need to make an adapter to be able to use the EEPROM instead of the kernel ROM. So let's have a look at that next. This is an Atmel AT28C256, which is a EEPROM, electrical erasable ROM. Well, electrically erasable programmable ROM. And this is what I'm going to use in my C64 to be able to use my custom kernel. To be able to do that, we have to make a little converter, because the pins are not completely compatible with the standard kernel ROM. This is the original kernel ROM from my C64. Its number is 901227-03, and if we compare these, you can see that one of them are actually bigger. So the EEPROM has 4 more pins. It has more address pins because it's a bigger chip. The pins on the left side of the EEPROM are the same on the original kernel. So both of the left side pins are the same. But on the other side there are some pins that are in a different order. So we need to make a converter for that. What I'm going to use is this, I don't know what's this called, like a prototyping board, perf board, whatever. As you can see, this board has columns, and it has 3 columns that are connected together in groups. So what I'm thinking is that if I make use of these connected pins, well, connected holes, I can put down the EEPROM like this, and then I can use the other connected holes to solder in a pin header at the bottom, and then I'll do the same on the far right side. I'll actually use a knife and I'll cut through the outer pin on the pins that are not supposed to be connected directly. And then I'll just use some jumper wires to connect them in the correct order. And I'm not going to solder the EEPROM directly to this, of course. I'm going to use a socket, and I'll just use these pin headers for the underside. So something like this. So I'll put the socket down, I'll solder in the pin header, offset by 2 columns, so they're still connected together, but then I can use these outer holes here and put 1 more pin header in, but then I'll just cut the traces on the pins that's not supposed to be connected, and then I'll just use some jumper wires to connect up the rest of the wires. So as you can see, I already did this, and the plan was to do it once more and actually record the process while doing it. But this was actually a pain in the ass to do. But I'll go through what I did and try to show some close-ups on the microscope. So this whole row of pins is just directly connected through the traces on this perf board, and on this other side, if we take a closer look at these 3 top pins here, are all VCC. So this top pin is VCC on the EEPROM, and 2 pins down is VCC on the actual kernel ROM. But they're all tied together, and the reason for that is that this second pin on the EEPROM is the write enable pin, and that's active low, so that's just tied high to prevent the chip going into write mode, basically. These are some extra pins tied to ground. This is address pin 13 and the OE pin on the EEPROM. So they're just tied to ground as well to prevent any issues with the address bus or the OE pin. So the tough parts in making this is the short wires, and there is not much space in between here. As you can see here, I offset the headers by 2 pins to allow myself some more space, but it's still hard to do. And down there, that's where I cut the trace. So there's no connection between that solder joint there and the inner pad. So that's cut. And it's the same for these pins down here, which are rearranged to the correct signals. So it's hard to see, but I used my multimeter to make sure there's no shorts and no connections where there are not supposed to be connections. So what I do now is just take one of these EEPROMs, put them in my newly acquired TL866 programmer, and then I just flashed the modified ROM onto this chip. I've opened up the XG Pro software. Let's load our kernel into the program. We can scroll down to see that this is the Merry Christmas kernel. As you can see here, we have the correct EEPROM selected. So let's just go to Device and Program. Let's go. There we go. Seems to be okay. We can do a device verify as well. Yeah, perfect. So our EEPROM should be programmed. So let's go back to the bench. Take it back out. We're getting close, so we'll continue with removing the stock kernel, which is this chip right here. And then we will insert the adapter we just made. So that goes in there. The final part is to just insert the EEPROM into our adapter. That looks nice. And then we'll just power on the C64. Let's power on. Would you look at that? There we go. Merry Christmas 64. That's really cool. So we modified the kernel ROM, put in an EEPROM by using a custom-made adapter, and now we're running off of our custom ROM. So the final thing we're going to do is load up the Commodore Christmas demo on our Christmas kernel, and that's going to be the end of the video. So thank you very much for watching, and Merry Christmas.